Okay, so in this video I'm going to consider optimization problems. We are in the script on page 6. So what is an optimization problem? Well, if we are dealing with an optimization problem, we want the value of something to be maximal or minimal. So this is optimization. I'm going to discuss an example in order to explain the theory behind these optimization problems. Well, here's the example. How long are the sides of a rectangle with maximal area whose diagonals are both 8 centimeters long? Okay, so here you see we want the area of a rectangle to be maximal. So this maximal means that we are dealing with optimization. So how are we going to approach this problem? Well, of course, since we are dealing here with some kind of geometrical problem, we are going to start by drawing a sketch. So we have a rectangle like this. Okay, what do we know about the rectangle? Well, we know here the diagonals are 8, so here this diagonal here is 8, and we want the sides here of the rectangle to find the sides of the rectangle. Okay, so we don't know anything about the sides at the moment, so this means we are going to introduce variables. And since we have two sides, well, we need two variables. We are going to use x and we are going to use y. So this side here is x and this side here is y. So what do we want? Well, we want the area of that rectangle to be maximal. So how do we calculate the area of a rectangle? Well, that's clear. That's just side times side, and this here should be maximal. Okay, so here we have a first equation describing the area of the rectangle. This equation is called the optimization equation. Why? Well, because this equation describes the area we want to be maximal. Okay? The problem with this area is the following one. Sorry, the problem with this formula is the following one. It contains two unknowns. Our next step is to eliminate one of the two unknowns. Well, how is this done? Well, we need a relation between x and y. How do we find such a relation? Well, consider the picture above. Here we have a right-angled triangle, so we can apply Pythagoras. So this gives x squared plus y squared equals 8 squared, which is 64. So this is Pythagoras. And now this thing here is my second equation. This is called the constraint equation, and it establishes a relation between my two unknowns. So the next step should be clear. I take the second equation, I solve for one of the two unknowns, and then I plug the result into the first equation. It doesn't matter whether I solve for x or for y. Well, I'm going to solve for y. So I start with my equation, and then I take the x squared on the other side. Then I draw the square root, leading to this. And now you see here I have a relation between my two unknowns, and now I can take this relation in order to eliminate one of the two unknowns from my area formula. So I'm going to take this and I'm going to plug it into the above equation, leading to a equals x times square root of 64 minus x squared. Now I have here a formula describing the area of the rectangle just with the help of one single unknown, namely x. So just one variable is left in the optimization equation. Well, what does this equation mean? Well, this equation tells us how to calculate the area of the rectangle if the length of one side is known. So this allows us to calculate A if the length of one side, x, is known. Well, this means that this equation describes a function with the possible side length as arguments, as x, and the resulting areas as values. So this here is a function equation, and I'm going to label that function f of x. Okay, so what do we want? Well, we want to find that value of x for which this formula here is a maximum. Well, what does this mean? Well, this means that we want to find the argument for which the derivative is 0. So we want to find that argument such that f prime of x equals 0. Okay? So, well, we could use this formula here in order to solve the problem. I'm going to use a trick, just in order to simplify everything a bit. So if x times square root of 64 minus x squared is maximal for a value of x, then the result of squaring this formula is maximal for that x as well, right? So this means I'm not going to consider consider f of x, but f squared of x. Why am I doing this? Well, f of x looks like this. Well, if we want to take the derivative of this, well, you see here we need to apply the product rule here, and then in addition we have this square root, so we need to apply the chain rule as well. If we square that formula, the derivatives get way more simple. So the only reason for doing this is the derivatives get simpler. So this step isn't necessary, it's just a matter of simplification. So let's see. F squared of x equals this. So I have a product, which means I can square both parts in isolation, leading to this. Now I can simplify this, leading to this. And you see here now we have just a polynomial, and we can take the derivative of that. So this is the derivative, and now as explained above, I'm going to set this thing here equal to 0, and now I'm going to solve for x. So x is plus minus the square root of 32. However, we are dealing with a rectangle and with the length of a side of that, so we can ignore the negative solution here, leading to x equals the square root of 32. The only thing left to do is to calculate y. Well, how am I doing this? Well, I have here an equation that allows me to calculate y, so I'm just going to plug x into that equation. And so this is also the square root of 32. So I see here x is the square root of 32, y is the square root of 32, and this is the solution of the whole problem. You see here, well, the rectangle is in fact a square. Okay, so here you see a general summary of what we are doing. Well, in the first case, you start with the optimization equation. Well, in most cases, the magnitude that is to be optimized is described with an equation containing two variables. Okay, you've seen this up here. The area of the rectangle is described by a formula containing two unknowns. Okay, the next step is the constraint equation. And what is this constraint equation doing? Well, that establishes a connection between the two variables. Okay. Then, next step is finding a function equation. We take the constraint equation, solve it for one of the two variables, and substitute into the optimization equation. The result is a function equation. And then, well, we use differential calculus to find the maximum or the minimum of the function. So we just take f prime of x equals 0. Okay, so this is it. This is how we approach these optimization problems.